Hi, today's video is brought to you by Capsule Simulations, and the topic of today's video is Martini force field and advanced coarse graining in biomolecular simulations. So today we're going to look into how to coarse grain a lipid membrane and how to generate a complex lipid membrane with this Martini coarse graining. So let's get started. So this is a website of Martini force field that we have. We're going to use this website and the force fields and stuff like that from here. So yeah, please bear with me then. Before starting, I would like to say that some of you might not have good computers and good computational facilities to run simulations like these can be computationally expensive, so you can do similar to what we are doing. We are currently using um, this uni data center facility, and they have some of the best computers out there. So yeah, if you want, you can use them as well. I'll just show you. So here you see I've just logged into my account, and yeah, this looks something like this. If I clear the screen, if I say node info, for example, these are some of the nodes that are available to me. For example, you can see it's a pretty nice configuration here, and the rate is very nominal. It's like less than 0.5 or 0.6 dollars per hour. So yeah, having such a great GPU at this price is really nice. 0.6 dollars or something like that. So yeah, please do check it out. I'll just also show you the link for how to apply. So it's unidatacenter.com. If you just go here, so this is the website. You can just go and read. But you, for applying, you have to go to this login page, log in your through your account, join the membership and stuff, and then you will actually get the login credentials from there. So yeah. Okay, so now coming to the Martini coarse graining thing. If we have to use, let's say, the first thing we need to do is download the force field parameters. So for example, I'm going to use Martini 3, right? There's this Martini V300 zip. I'll just going to copy the address link, and now I'll open a terminal. So as I said, I'm going to use this service for running this simulation. So just yeah, if you if you don't have an account, just create an account, then you can follow this tutorial, or you can try it on your own laptop. Okay, so we need to go to simulations, Martini. So previously I've tried some other simulations, so I'll make one more folder. Okay, so this time I'm going to create just a very basic, let's say DPPC based or DIPC based, you know, what do you call it, membrane. So it's just a single lipid membrane, a single lipid inside this membrane. So once we are inside, we have to now run a command which is insane.py. So you can have it from this website. You can go to this tool section and then other tools. I think it is here. Okay, maybe inside the tools you have to go to this protein and bilayers. Here you should find that tool, which is the Martinize is one of these tools. If you want to convert your atomistic structures to like coarse grain structures, then you have to use Martinize. Else you have to use this insane in cases where you want to like directly generate like coarse grain, lipid membranes. If you want to do that, like directly generate coarse grain lipid membranes, then insane.py is the file. If you go here to the GitHub repository and you check how to install it, so this is the way to install it. pip install insane. So I've already done it, but I'll show you. So I just have to write pip install. Uh, okay, I think this size is better, right? So pip install insane. So once you do that, it's already says that the requirements already satisfied, which means I already have this installed in my computer. So for you, then you have to just write insane, and then you have to provide a output like output file, which is bilayer.grow for me. You also have to provide an output topology file, which is topol.top for me, and then you have to mention how like big the simulation box should be. So I've provided 28 in the x direction, 28 nanometers in the y direction, and 20 nanometers in the z direction. So that's the size of my simulation box. It's quite big. Then we have to provide DPPC, which we are not using. So now we have to provide -L, which means in the lower leaflet what is the composition. So here I'll just provide DIPC, because that's what I said, that we are going to make a membrane just with DIPC. So here's the membrane DIPC. Now if let's say you want to have in the lower leaflet, you want to have multiple um, composition of multiple membranes, right? Then what you have to do is you just have to mention one more flag, which is -L. So this denotes that you are still specifying the composition for the lower leaflet. Then let's say I want to add DPPC. I can add it like so here I said DPPC, then colon 5, which means 50% of DPPC, and I've just put some spaces so that you can see the next line, and 50% of DIPC. So that's the way you have to show it. If you let's say have three compositions, so let's say DIPC is 3, and then another, there is something called, let's say just I'm just making this up, let's say DYPC, there's something called DYPC and that composition is 20%. Then you have to provide it like this for the lower leaflet. For the upper leaflet, you have to still do that in the same way that I've shown you. If I then create, let's say like this, then the membrane that they will create would be having 100% DIPC in the upper layer, and in the lower layer there would be 50% DPPC, 30% DIPC, and 20% DYPC. So this would be the composition of that then. So but we don't want to do that. This we want to have a very simple membrane. So it's going to be completely DIPC at the lower leaflet, completely DIPC the upper leaflet. Then you have to provide -Sol and in caps W. Also for example, let's say you want to generate different type of solvent, then you can also provide Sol WF. This can also be done, but you don't need that. Again, percentage wise, you can put this anti-freezing water, you know. Sorry, this would be then 9, this would be then 1. So you can also do that, like 90:10 ratio. You can add some anti-freezing water, but you don't need that in Martini 3. So yeah, I'm just leaving that out. So once I now press enter, I should get the structures I'm looking for. So you see, it have created these two files, bilayer and topol.top. So I'll just clear that. Okay, so now I'll just open the file and show you how it looks. So there are about 1,30,000 atoms, not atoms, sorry. There are 1,30,751 beads. So now these are like group of atoms. So this one line that you can see here, in atomistic simulation, this used to represent one atom, but now it represents a group of atoms represented by a bigger bead. So what is a bead? Bead is basically a spherical object that occupies the area of more than one atoms. So if it occupies more than one atoms, then we call this a bead. Okay, and similarly there are like these many number of beads, and the rest of the groove file looks exactly the same as atomistic simulation. There's nothing change. Okay. Okay, so now we have the bilayer, we have the topol.top as well. So I'll show you that as well. So we have the topol.top as well. Now just notice that this includes a martini.itp, but we don't have it so far, right? In the directory we don't have any martini.itp. So you remember we have copied some link at the beginning. So yeah, that's the link. What we'll do wget and then paste the link after that. So this should actually download the folder for you. So let's just wait for, yeah, now it's done. So we have to untar this. So tar and then xvf and then martini. Sorry, okay, so this is not a tar file, so I was like untarring it, but okay, this can be done with unzip. Okay, you see it's done. What we can do now is we can have to go to the inside this folder, and here we can see there are multiple ITP files, and one of them is this ITP that it have included, but we would need more than that. We would also need the phospholipids. If we have added some ions, then we would also need this. So what I would do is I would just add all of them, just in case if there's any atoms being present from any of these ITP files. So for that I've actually previously done that, so I'll just so here's basically some lines I've wrote. This basically represent all the ITP files that you have seen. Okay, sterol one is not there, but we don't even need that right now. So yeah, we can go out and we can put this inside our topol.top. So now we have just added that and we save it. So basically your topol.top looks like this now, and this is enough. Okay, one more thing you need to note is I'm using VI. I'm not sure if you guys are familiar with it. So for people who are not familiar with VI, I'll just say one or two lines. So once you open, VI, like VI space topol.top, you get this view. Now if I try to type something, no, it doesn't work, right? So it will do nasty things if you just don't know what to do and try to type it. So firstly you have to press I. The moment you press I, look in the like left lower corner, it goes into insert mode. When you press I, it goes into insert mode. Now you can type anything you want. It now in the typing mode, right, or insert mode. So once you are done, you have to press escape. So see, insert mode is gone. Then you have to press colon WQ, which is save as you are leaving it. So save as it is. So that's the thing. If let's say you have typed something wrong and you don't want to save, then you will say quit without saving. So this is Q exclamatory mark, colon Q exclamatory mark is quit without saving, and WQ is quit with saving. Okay, so now we have the topol files as well. So we just now need to have GROMACS. So as I was saying, like if you are using your own computers, then you would probably need also an installation of the GROMACS. But to my help. These services also provide, like these GROMACS installations are already there. If you want to install something else as well, just tell them, they'll do it. So it's really convenient for us. So you see, it's like, if I now want to use, okay, I'll first show you. See, I don't have any GROMACS here. If I want to use a GROMACS, which is, let's say, module load, I want to use, let's say, this one, right? So I'll just write GROMACS 2023.3, press enter, and you see we have the, like, it says loading GROMACS and then also loading CUDA. So now if I just go and check GMX minus H, it gives me the output that I wanted, and see, this is 23.3. If I, let's say, want to change it, then I have just to say a module purge, and that, and then let's say module AV, and choose something else like this 24.3. So I'll just go and say 2024.3, and now if I just go and say gmx minus h, you see 24.3 has been loaded. So it's that simple to change, different versions and stuff. So yeah, so now we are using 2024.3 GROMACS, and we will try to move forward. So our goal was to run, to generate a em.tpr to run the energy minimization. So I'll just write gromp minus h. Okay, so these are some gromps I've run before. So yeah, here, so gmx gromp minus f em slash em.mdp. Okay, there are some folders I've created before, so press enter, it's gonna give error. What I'll do, I'll create a folder named em, and I'll also copy, some em or energy minimization mdp files. So okay, so if I now check, I have the em.mdp file. How you can get it, I'll also show you that, so you don't have to see and type. You can write, okay, I think if I go back on this page, I'll land up in the, yeah. So you go to examples, you go to lipid membranes. Okay, now this, okay, you go to tutorials. I think in tutorials you will have it. In the hands-on tutorial, you go to self-assembly here, press start tutorial. Here you will have one of these files. So yeah, this one, bilayer lipidome tutorial, GMX 5 2027 August. This, so inside this file, I probably have downloaded it before, but yeah, I can also download it again. Inside this like folder, you will get a lot of files, and we are going to use some of these files only. Okay, so let's just wait for this to finish. I think this is very long. Okay, I would rather not wait, and I'll just tell you what's inside. So basically, inside that you will get some files like, I'll show you. This is another folder that I've used, and inside that, so firstly there is this em.mdp. I think in that folder the name would be minimization.mdp or something like that. But then, sorry, my bad. So this is one of the files that you want to use. Also, please note that I have not used them as it is, so I've made some changes. So just please look into the changes I've made while copy pasting from that folder. The other files you might want to use is something like relax1.mdp. This is like basically one nanosecond, 1 picosecond thing is there. So basically they have named it relax 1 because of I think the femtosecond level timestamps they have, or the time steps they have. So it's like 1 femtosecond, that's why they have named it relax 1. So firstly we will run this, we will relax the system with 1 femtosecond timestamp for 1,000 steps, which is about 1 picosecond or so. Then we will use the relax 5.mdp, which is here 5 femtoseconds. We run it for 10,000 steps, which is about I think 50 picosecond or so. After that we will run it for 10 femtoseconds. So there's a 10 relax 10 script where we have this for 10 femtoseconds, and we have this for 10,000 steps, which is about I think 100 picosecond or so. And after that last minimization step, which is relax 40. So you have it for 40 the time step is 40 femtoseconds, and you run it for 1 lakh steps, or 1 or 0.1 million steps, or 100,000 steps, right? 100,000 steps, 40 femtoseconds, that comes to about 4,000 picoseconds or 4 nanoseconds or so. So these are the four relaxation steps you have to do before doing the MD, which I'll also show you. So it's MD. Okay. Oops, this should be here. Yeah. So you see here we have about, this is like 100,000 here, and you see it's a big number, right? About 3, 3, 6, 7, 8, about 8 zeros is a big number. We want to run it for about, if you multiply this timestamp with this, we will get about 3 microseconds or so. So this is a big number. We want to probably run a smaller run for this video, but I'm just showing you, and the other things you can check in the check below. I'll show you all of them one by one now. Okay. So here I have created the EM folder. I'll also create relax 1, relax 5, relax 10, relax 40. So these are the 4 relaxation steps we need. Then we need a MD run. So yeah, these are the 4 relaxation step, and then you have one MD run. So 5 runs done. Great. So let's start with relax 1 then. I'll just copy in the, oh, we have got the EM file first, right? Yeah, we have got the EM files. So I'll start with that. GMX GROMP. So now you see we can see everything else is there. I press enter, and it says sterol not found. Yeah, you remember while I was talking about that, I said that sterol file is not available here. It basically was not in the original Martini. I have to download it from somewhere else. Some other researchers have independently provided this sterol ITP. So yeah, now if I run that, it should run. As you see, it's giving me no errors. It's working pretty fine, which means I can now run GMX GROMP, GMX MD run, then def nm md/md. We press enter. Oh, sorry, we were working with EM, right? Sorry. So yeah, it's not showing me some outputs, but if I just write V, then it will be in the verbose mode and it will also show you that something is being done underneath. Okay, so the EM is done. So we'll just go inside the EM folder and we'll just check em.log. So always check the log files. It gives you some, really nice, interesting facts about your simulation steps. So it's saying the potential energy did not converge to F max 10 in 1000 steps. So yeah, we might want to. So we can and we cannot. So I mean the force is still very high. So what we can do is we can do. Okay, we are already inside that. What we can do is we can increase the number of steps. So let's say instead of 1000 steps I provide 5000 steps and I go back and run this energy minimization again. That way I'm trying to ensure that the force actually comes down to a stable number. Okay, so this is taking a lot of time. So what I'll do is probably I'll probably cut it. There's another way to do it. So I'll just create a submit like run.sh file. The first line needs to be bin/bash, and then I have to provide the partition equal to, let's say, red. There needs to be sbatch as well. Partition equal to red. I need to now you remember the module load command. So module load GROMACS 2023 sorry 24.3, and then we write gmx md run defnm em/em. Yeah, so what I do is I'll just check if we have the node free. Yes, you can check it through its info. So you see the red partition, it's idle, which means it's available. So we'll just say as batch run dot a. So now you see there's it says submitted job 763. If you check the SQ, it's also showing me that has been submitted to the red node, right? 763, this one, it's running. um, if I check, let's say node info, I've shown you, right? So the red one is this node is that we have about 32 vCPUs here and about 4090 here, so it's really fast. About 16,000 CUDA cores, 24 GB VRAM. So this is going to be really fast, and cost would be less than like 1 or 2 cents for running this energy minimization. So we don't really have to worry about that. Okay, yeah, see, it's already finished. Like on the screen, it was taking so long time, but now you see there's no job showing, which means it's been finished. So if we look less em.log, we go to the end, and it still says that it did not converge in 5001 steps. But now, if you remember from the last time, we have these numbers to be 10 to the power 3. So we have like decreased the energy maximum force by like 10 times, which is pretty good, I would say. I'll try to show you which one that was. I think it was log 2. Yeah, here in 1001 steps. You see, it was 10 to the power 3. So we are doing pretty fine on that. Like decreasing the energy by 10 times, it's quite good, and I think we are in the reasonable limit that we can move forward. So yeah. Now moving to the relax one. Um, so this is the one that now we need to work on. So firstly, we need to copy the MDP files. I'm going to copy it from my older folders. So we have the relax one, then .mdp, put this into relax one. So I'm not sure if you are familiar with Linux, but what's basically happening is we are using a copy command, cp. We are first providing the source of this file, and then we are providing the destination. So that's like very simple thing. If you don't know, you can like check our blogs, there are our videos, there are like a lot of things we have provided on how to use Linux commands and stuff. So yeah, please do so. Now we need to do gromp on the newly generated um, files. So okay, in the meantime, we can also create a index file. So I just came to my notice that I was using an index file there. Okay, I need to see the, okay, it takes two flags, minus f, and here it takes the confirmation. So I'll just give the newly generated confirmation from the energy minimization, and it takes an output, which is index.ndx. If you have already have an index file that is lying around with you and you want to pass that to generate a new index file, then you can also do that. But I don't have any, so I'm creating it from new. So I'll just use it like this. DIPC water, I don't need anything else. So Q, press Q and then enter. Now it will get saved. If I check, I should have a new index file here. Great. So now if I go back to gromp and I run this for, so just check out the command. It's gromp minus f, then the mdp file, minus o, then the tpr file, minus p the topol file, minus c with the structure file, minus n with the index file, and then a max one. Basically you can remove the max one when you're trying out for the first time, but sometime it can happen that you get some errors. So errors like what? So these are like some very old, kind of errors that we kind of know. that we should refrain from Benson because it's not strictly doesn't generate the kind of ensembles you want to use. So we kind of know that, but also since this is a relaxation step, we don't want the ensembles to be strict, like strictly following the thermostat and the barostats. There would be some artifacts, right? Why? Because what Berenson does is it basically is a soft, a soft thermostat and soft barostat. That's basically how we define it. And in the relaxation step, that's exactly what we needed. Even if let's say if the energy is high, when we increase the temperature, there's some part which, gets a lot of like gathering of temperature. We need it to be, deformed and do a little bit like increasing the temperature and stuff. That can be done with the Berenson. The temperature would increase and it will actually, like deform and get a shape it wants. But that's not possible with the strict thermostats and barostats. They're like very strict in what kind of temperatures can be maintained inside. So yeah, for the relaxation steps, maybe this is what we want. So let's just move with that. What we will add to correct this is we will add max one 2, and that will now generate the files. It says 17 MB of file data will be generated. So now we just need to write, okay, again we will submit this data run to the node. So we will say, what do you call this, md, no, that was relax 1, and this was relax 1, if I'm not right, and if I'm not wrong, this was it. Then there's one more thing we can add is nb GPU. So we are specifying that it should use the GPU. Let's check. So whenever you run a new run, no, it's gets the output here. So just check. You see, this was a 1 picosecond run, and it finished even before we are able to check. So this is really insane. Like it, wow. Okay, now let's just check if the files are there. You see all the files we have got. Okay, now we need to do the next step. So we need to copy the MDP parameters for relax 5, and we will copy it in the relax 5 folder. We need to run the grom command for relax 5. And just notice one thing, so I've already run it, it will generate about 73 MB of data. But notice like the MDP from relax 5 folder, TPF from relax 5 folder, topology normally, right? And then you have the structure file from relax 1 folder, which means every step you go ahead, you keep on using the latest structure file that you are using. This is basically what we do kind of. So you can also follow this method and don't rely on like the first structure that you have generated. Just keep on updating the structure. Then you have also provided the index file and max one. So I've already run that in the here. So we have it. We now want to change from this to relax 5. We say s batch. So now it's see where it's running, and now it's finished. So relax, it was 5, right? So you see it's already finished. So we can actually move to the next relaxation step. Now we need to copy the relax 10. So is the command for relax 10, just have a look. Okay, in the relax 10 we have copied it, but in the MDP file we need to make some changes. Clearly here we only have DIPC at this moment, so that will be it. And in the energy groups, where is energy groups? Okay, now if we run it, it should run actually. Yeah, so let's just go back and change this to relax 10. Whoops, this might have also finished. So let's check relax 10. I think it's relax 10 dot log. So yeah, it's also finished. You can see the performance here, right? um, I think it's still not in the best performance. When we run longer runs, it will get more performance. But even in these small runs, we are getting about 2300 nanoseconds per day, which is insane. But I think these systems should get more speed. So let's just look into the other ones. Now we need to copy the relax 40. This is the last relaxation step. I mean, I'm also getting tired with you. So yeah, please, I mean, if you get the concept of these relaxations, then you can just skip ahead and go to the production run step, because there I will share some important facts. So here, okay, right, GMX GROM relax 40, yeah. So I run that. Okay, this also have the same issue, which is that needs to change in the relax MDP, that we need to add here. Yeah, now it should run properly. So we have to do this relax 40, relax 40. So now you can see it's running. Probably it will take a couple of more seconds before it finishes. So let's just follow it. Great. The run has been finished. So with that, our final relaxation steps were also over. So we are very close to running our MD run. We check the, yeah, that's what I was talking about. So we ran it for a little longer and we are getting a benchmark of 7,800 nanoseconds per day, which is about 8,000 nanoseconds per day. That's the kind of speed you can get out of these machines. So just think about it, 8 microseconds per day. This is huge. Great. So we have our simulations done. Now the final step, which was copying MD320. We'll copy MD here. Okay. Right, we have this MDP file for the production one. I'll just reduce it from so that's kind of it. Yeah. So this is about 1 million steps. So I'm assuming this to be how much? 30,000. So it's like 30 nanosecond run. What we are currently showing up here. So this run will run for about 30 nanoseconds or so. We have to also remove this DPPC from here, and let's just try. Here this will be just MD. This will be MD as well. I can add one more command, which is update GPU. Why have I used this command update GPU? So this basically runs the run in GPU only mode, which is like non-resident GPU non-resident run, which is basically like you are not taking the code out of the GPU again and again. You just the code stays inside the GPU and runs inside the GPU only. So that makes the simulations much more faster. So yeah, we are now ready for the production run. Okay, great. Now it says it will generate about 28 MB of data, which is nice. I mean, you are worried why so, right? Why only 28 MB? So I'll show you. We have we might want to change some settings here. So you see the total number of steps that we are going to generate is about 100 1 million, sorry, 1 million, or yeah, in India we might call it about 336, about 10 lakhs or so, right? Now coming to this output, right, this determines how big the file was and after how many steps you're going to save one step. So here has been set to 100,000. So this will only save about 10 copies of frames in that. So I'll just probably change this to 1,000 so that there would be 1,000 different frames inside our trajectory. Now if we run it again, it will now generate about 645 MB of data, which is fine for us. 1,000 frames is fine. So let's now go for this. I think this is now set. If we do as batch, now you see it's now running. So we'll just watch. It's probably a few seconds. It should not take more than a few seconds. So yeah. Okay, let's check how much has been done. So about 4.8 nanoseconds has been done. We need to reach about 30. So yeah, this is gonna take 1 or 2 more minutes. So you can actually just skip it like 2 seconds or 2 minutes later. You can just skip that. Okay, so in the meantime, I can also tell you something else about Martini. So this is a slides from Paulo. So all credits to him for this. I mean for the slides. Yes. Okay. So I'm assuming that you guys are new to this simulation world, right? And also to this Martini beading, right? So that's why I thought of like showing you this. Probably I should have shown you this in the beginning, but yeah, it's very interesting. So what we do in the atomistic simulations is that this red kind of thing that you see, this is like a water, right? There's one hydrogen here, one hydrogen here, and one water here. So I'm not sure if you're able to see. Probably this is better. So this is a water molecule, oxygen, hydrogen, hydrogen. So what happens in Martini with the water is that you now take 4 water molecules and you make them a bead. So how many atoms? So 4 oxygen atoms and 8 hydrogen atoms, which is about 12 atoms. So you take 12 atoms and you make a bead in Martini. If you look into how they describe something like what do you call this, benzene kind of ring. So they have taken like these 3 atoms and um, they have used this 3 beads to show you a toluene, right? Similarly here, as you can see, a whole phosphate molecule which is like PO4. So that has been shown with 1 bead, and here a lot of atoms are merged together inside 1 bead. So they're like different type of beads. I think they call it like 3 atom beads, 4 atom beads, and probably there are also 5 atom beads as well. So approximately 4:1 mapping has been done of non-hydrogen atoms. Um so yeah, here. So there are, yeah, now coming to, what you have seen at the top is basically just the size based beat classification, right? Now they have also have charge based beat classification. So now they have something like a non-polar beads, intermediate beads, polar beads, charge beads. Also, depending on what kind of purpose that serves, they have different bead sizes. So tiny, small, regular, just like pizzas, right? So this is kind of very interesting in that. So I would really ask you to go through these slides. There are many actually, and you would definitely get to learn something out of it. So yeah, please do so. And our simulations are still not over, so we'll just check what's the status. It's already done. I mean, not already done, but it's almost done. So it's 24 nanoseconds has been done. We have targeted for 30 nanoseconds. So that's about 6 nanoseconds apart. A few more seconds. So by that time, let's look into Martini lipids. think that would be interesting. So the credit for these slides goes to Manuel Mello. So I mean, yeah, this is pretty nice. So um, like why Martini simulations are faster? So Martini simulations are not faster just because we are reducing the number of atoms. Like let's say they were like in the all atom simulation there are like 50 atoms. When you take 4 to 1 mapping, or let's say there were 40 atoms in the all atom simulation, if you take 4 to 1 mappings in the Martini, you will have 10 atoms, right? So somebody will say, okay, Martini simulations are usually faster because they have less number of atoms. But a very wise professor once like taught us this, and that's how I kind of remember it such a long way around. That it's not just about that; it's also about if we look into these timestamps. So if you look into the timestamps in the all-atom simulations, these are usually in the femtosecond regime, right? In the one of so it's usually like 0.002, so that's like 2 femtoseconds. But now we are using about 30 femtoseconds as timestamps. So that's how many jumps, right? That's like 15 times faster. So we are increasing the speed 15 times faster here. We can even go higher, like we can even go 40 femtoseconds, and that would be like even higher, like 20 times faster. So we are going 15 times faster from atomistic simulation here, and we are going um, like 10 times like 4 times faster in the number of atoms. So we have reduced the number of atoms by 4 times, so we are going 4 times faster there. Like these are like usually very crude answer, right? We are not going into details, but it's like approximately 4 times faster due to now less number of atoms, and 15 times faster due to increase in the time steps. So that's huge. Now one might ask, I think some of you are already having this question in your mind, that why can't we actually put in the atomistic simulation, since we have this 2 femtosecond, sorry, since we have this 2 femtoseconds 2 femtosecond time steps, why can't we increase that 2 femtoseconds to larger numbers like 20 femtoseconds or 30 femtoseconds? Why can't we have that in the atomistic simulations? The answer is that you need to capture a very essential part, like essential motions in your simulations, else the simulation will crash. For example, let's say you have a CH bond, right? Or a OH bond, right? The hydrogen, basically something attached to hydrogen. Since hydrogens are so light, it moves at a certain speed and at a certain revolution per second. It like does that. If you check that, and if you use a 2 femtosecond in all atom simulation, since we have hydrogens there, um, if you use 2 femtoseconds, then in one oscillation you will only be able to capture the motion of hydrogen like 2 or 3 times, or maybe 4 times. That's like it. You cannot capture more than that of like motions of hydrogen. So we cannot go beyond 2 femtoseconds in the atomistic simulation. But in the Martini simulations, we have no hydrogens. They are all beads, even not just atoms, but all beads, right? So since we have um, such a freedom that we don't have hydrogen, so we don't need to capture in that regime. Like we can come out of it, and we can play in the bigger the molecules, slower the movements, and slower the time, like slower the time steps, right? I mean, here the time step was just 2 femtoseconds, here's 30. So yeah, that was just the context. But the context is also that our simulation is done, so we'll just check that. So here as well you see 6400 nanoseconds per day, huge speed as I was saying. So now our simulation is done. We will also try to check what the, okay, not this maybe, or maybe this, I don't know, md dot um, grow, like this is the last frame that they have generated. So since this is a server, right, it's not as my computer, so I cannot use something like vmd or so. So what I'll do is I'll make another video on visualizing the same thing, and I'll attach it to this the next part of this video. So basically that would be like uh, two videos in my playlist, so just go and watch the next video, and yeah, have a nice day then. Also, what I would suggest is, if you are, low on computational resources, if you don't have a good computers, if you don't have a good laptops, check that out. I think they are on a mission to provide university researchers with really nice facilities. That's how we got connected to them. So yeah, have a nice day. So with them I mean Unida Center. So yeah, have a nice day and see you on the next video then. Bye bye.